I'm Gavin Key. I'm a principal engineer for network architecture at Crusoe. I'm going to talk to you about the pragmatic side of just what Amr and Tam just talked about. We are not an emulation company. We're a cloud. We're a vertically aligned, sustainably powered AI infrastructure company. And we source environmentally aligned power sources, whether that's wind, solar, geothermal. I'll talk about some of the projects to give you some context on these. On top of that, we build AI data center infrastructure, and we have probably one of the biggest projects on the planet happening right now in Abilene, Texas. It's a gigawatt scale campus, and we have a world-class digital infrastructure team who are leading that. And that group also, they source the power, and we take the compute to that power wherever it is in the world. On top of that, we build our AI cloud platform, and that's our infrastructure as a service. So today, customers will typically consume GPU supercompute via virtualized machines. And then on top of that, again, we build managed AI solutions. So AI as a service, inference and workloads would be one example. The work I do at Crusoe is kind of being from the blank whiteboard, bringing Crusoe Cloud to life. That has been design and engineering of the data center networks, the software-defined networking that sits on top of that, and the GPU to GPU fabrics, InfiniBand, etc., all fully real optimized NVIDIA reference architecture. And our mission is really to build the world's favorite AI cloud. And we're purpose-built for AI. We have enterprise scale infrastructure. So you can get anything from one GPU to any number of thousands of GPUs in a single fabric. We have a world-class customer support. That's one thing in this problem space that's so fundamentally important is support, because GPUs, these systems are massively complex. There's a lot going on. There's a lot can go wrong. You need to respond quickly because this is so capital intensive. Customers trust us to both help them train and also inference. So if any infrastructure problems happen, we respond 24/7, 365 as quick as humanly possible. And because we source power, we're vertically integrated, we feel we're more cost effective and sustainable as a platform.
You talk about the sustainability and source power. Are you co-locating close to power? Is that your thing, co-locating close to the power systems?
Yes, or building the power systems themselves. So, a good example of a project, I'll introduce it in the next slide. We'll give you some examples of how we take the compute to stranded energy. And, with these systems, they're like so power intensive, that you can't just go to a metropolitan area and take a typical data center facility now. You need in the tens of megawatts, if not hundreds of megawatts of power to build at scale. So I'll show you an example of two of these shortly.
Excellent.
I just want to call out some of Crusoe Cloud customers. We have some amazing customers on our platform. And, one thing I'm particularly proud of is the fact that, we are customers of our own customer. So like Codium are sort of rebranded to Windsurf. Most recently, I used their AI coding assistant. It's awesome. But we have a range of customers doing absolutely amazing things on our platform. Descartes building world models. You can go on to Descartes.ai. go interact with Minecraft that's powered by Crusoe on our platform. And all of that inference and workload is done out of an environmentally aligned data center that we have in Iceland using geothermal power. And this is just an example of like the first facility I ever worked on to bring Crusoe Cloud to life was using digital flare. So we call it digital flare mitigation. So we would build our own modular data centers, and we take them to remote oil fields, and we build the turbine capacity to use that gas that's otherwise flared into the atmosphere. You would see them in oil fields, just those big torches flying. Instead of burning that, we combust that in generators, and we power the GPU compute on site with that. So if you've seen where these places are, it's kind of amazing. It's just in the middle of nowhere. It's the operating conditions are really harsh during the winter. We have amazing oil field operations teams who work in all environments to ensure that we can keep that uptime on those sites. During massive storms, of course, if there's any disruption of power to the oil field operations themselves, we can flip between different power sources on site, and we can even gracefully take down a whole site if needs be. Renewable energy sources. So something like I mentioned there, one of our facilities is in Iceland. So we use geothermal power there. Again, Iceland has an abundance of energy. So we take the compute to where that energy is, and we build the backbone infrastructure to connect our customers from either mainland Europe and the US into that facility.
Quick question.
Yeah.
Brian Martin, Signal 65. How far into that backbone construction do you get? You actually doing undersea cabling? Or are you leveraging existing cabling?
Oh, we will definitely leverage, third-party providers that offer those subsea cable systems. So we will go to, major providers of that infrastructure, and buy up to 400 gigabits per second of capacity on any of those. But we'll use multiple different providers for redundancy. What we'll talk about here very shortly is like I remember Tom was talking specifically about how data hungry GPUs are. You've got to feed them a massive amount of data, and you got to do it in a timely way. And data is distributed among many different cloud providers. So if you need data to move from US East and your S3 bucket into a site like Iceland, we need to do that with high capacity, low latency links if possible.
Yeah, I worked in a renewable energy company for a while, but you might want to explain what digital flare mitigation is, because it's not something that everybody's going to understand.
Yeah, I think it's a good question, because I kind of like assume that everybody knows that this is a Crusoe branded thing. Digital flare mitigation is just like our term for, using that flare gas to power our compute. So instead of that, burning that flare off into the atmosphere and all the toxins and all the bad things that come with that, just actually running that into our own generators and being our own power source on that site.
It has to do with like methane capture and
exactly. Yeah.
Okay.
Yeah. So let's talk about accelerated networking on Crusoe Cloud. So one of the things that I'm going to talk about today, I'll not talk about backend networking here, which would you consider that GPU to GPU. Alex as well is going to cover that, but I'm going to talk about accelerated networking on Crusoe Cloud. So what it is that we're trying to do is, it's a really true cloud experience. So we build a multi-tenant infrastructure. So we have many different tenants running on top of the same physical infrastructure, and we want to accelerate the customer workloads onto the hardware for the maximum amount of efficiency. The reason is like we want to give the customer the most amount of CPU capacity. We don't want to be using CPU for shifting network traffic around, we want to do that in hardware. So we implement virtual private cloud networking, and this is just a simple mental model that you can use for this slide. So each of these hosts down here have different tenants located on these compute nodes, and we basically isolate those tenants over secure overlays. And today we use Geneve as an overlay layer. And what that means is like we have to basically build a software pipeline that implements logical routers, logical switches. It implements things like DNAT and SNAT, load balancing, and of course security using access control lists and firewall rules. And as I said, this whole logical pipeline today is accelerated using the NVIDIA ConnectX SmartNICs, and more recently we're kind of working to bring the Bluefield 3 to life. And then of course, on top of that, we have software-defined storage for obviously moving data into these systems.
Can't believe it's I'm the storage person here, or a couple of others are. What are you using for software-defined storage?
So we use a combination of things. So for block storage, we partner with Lightbits for software-defined storage. That would be for block, and then we use VAST for file systems and S3, etc. So we'll talk about data path acceleration. So in the previous slides, what we've seen is there's different contexts in which packets move in this infrastructure. It's either we can consider that north-south, as it basically egresses from the customer's overlay or VPC networking, or east-west, where it's encapsulated within the VPC networking across nodes in the infrastructure. This is a mental model basically of how this logical pipeline is implemented. So customers have VPC networking, they have distributed logical routers, they have distributed logical switches, they have all their DNAT and SNAT rules implemented in these logical router pipelines. There are firewall rules implemented in logical switching pipelines. And these all have very, very specific requirements. So if we would need to accelerate this, our goal here is to reduce overall latency and CPU overhead while we process a lot of packets through the system. We use stateless offloading for that east-west traffic within that Geneve overlay, and we offload that onto the CX card. We also have the stateful operations challenge. So like I mentioned, as you egress from the VPC onto the physical network to get to services, whether that's S3 or it's just the general internet, whatever it is, you actually have to go through a connection track pipeline. So you're actually using an access control rule, or you're using a NAT rule, so you can be routed on that external network. So that's a really complex thing. The performance impacts that we're really trying to mitigate here is like the high CPU utilization and bottlenecks as a result of that. And again, the goal is to efficiently accelerate this onto the NIC hardware. And we're getting close to the point where we can really start to talk about how we have went on this journey from initially optimizing our pipeline to implement multi-tenancy VPC networking to optimizing that further. So, I mean, you can go and use Open vSwitch, and it's purely a software switch, layer 2, very simple. You can accelerate that onto an eSwitch on the NIC, and you can do this all using a kernel pipeline where we have both a slow path and a fast path. We're going to talk about this. I'll show a slide next that'll really illustrate this. This slide shows you a journey that we went on in terms of like efficiently building our cloud platform on this front-end networking. So we found that as we used OVS kernel, the slow path can become a bottleneck at very, very high connection rates. Why does that matter? Because you're moving from a world where when we started, everything was based on training. there were no cool models that you could really use for inferencing. Now there are a lot. So the world is changing from just model training to actually serving these models through inferencing. So the workloads really are starting to change.
Question.
Yeah.
The question about your journey here through kernel to Docker. Did you also do some DPDK mode testing on OVS?
No, because connection tracking on OVS DPDK is just not fit for purpose
Gotcha.
for what we need. That's a good question.
Another question is, at this point, what's sort of your mix that you, for Crusoe, of tenants that are doing training versus inferencing?
So there are multiple different types of customer. Some obviously will train and then they'll serve their own models. Other types of customers will resell compute and customers will come and inference on them. And then there's, of course, ourselves building our own inferencing and sort of managed AI services on top. So our own internal customers. But many customers will both train and inference because, of course, if you've got all this expensive compute, you're really going to put it to use and try and drive some revenue off it. So OVS Doka, what is Doka? It's NVIDIA's data center on a chip architecture. And yeah, there's a lot of acronyms I know in this networking space. Yeah. So the journey that we went on was, okay, so how can we optimize for the hardware that we actually use? We don't build our own smart NICs. We were a very small team when we started this project. We're growing very rapidly. But we leveraged like the help from NVIDIA quite a lot. And our attempt was to really improve the efficiency of the system and to facilitate these moves towards more inferencing-based workloads. And our attempt here as we move from the OVS kernel pure open source world to actually using more of NVIDIA's stack to optimize was, okay, how do we test that? How do we know, based on our operational experience, that Doka is going to serve the needs that we have? So we're really attempting to get to initially like high connection per second rate of about 30,000 connections per second with 1 million in hardware, and ensure that under the most extreme load that we are able to understand that the system will behave in a deterministic way. This slide shows the differences in these two models. It's like OVS hardware TC offload to OVS Doka hardware offload. They're essentially very similar data paths. Of course, you have slow path and you have fast path. Anything that's not this blue line at the bottom here can be considered somewhat the slow path, right? It's exception packets, it's the first packets in the flow, and we really want to test what the difference is between these two pipelines and what the impact of these is at scale. The end result is we're trying to really do the same thing, but at very, very high loads, we're trying to ensure that the determinism of the system remains. So this is where I met my friend and colleagues, I would call them, because we work very, very closely with the Keysight team. We looked at how are we going to actually test this to ensure that we can pull the system apart, that we can ensure not just the performance of the system, but the stability of the system under extreme load. So we came up with, a testing setup using SciPerf as a tool to generate stateful traffic through the system. This is a contrived sort of example of how we tested this. So we come up with a topology that really exercises the code path, and then we use SciPerf as the traffic generator to ensure that we can really exercise that data path at scale. So I would say probably the journey initially was like we didn't really know how to test. We just knew that what we wanted to test, right? So part of the exercise in working with the Keysight team was really understanding the behavior of the product, and being able to actually generate stateful traffic is massively important to us. Why? Because we don't know the customer workload ahead of time. So we have to build a contrived pipeline in order to stress the system as much as possible. So we simply start with just some simple throughput testing and measuring the impact of that on the system. So with SciPerf, we're initially just able to look at our virtualized infrastructure. I'll just skip back here 1 second just to call out here is what we have in virtual machines is SRIOV. So this is directly connecting us to the NIC hardware. And in order to achieve the data path implementation, Linux has a switch driver model, or we can implement the kernel bypass with NVIDIA's OVS Doka framework. And when we want to test the behavior of these two systems, we want to run the exact same test, right? And SciPerf allows us to do that. But not only does it allow us to do that, it allows us to kind of modify all the different parameters that you have. So for example, we might test with very, very small packet sizes. We might test with jumbo frames and kind of look at what the behavior in the system is as we change those different workload types. So a throughput test, we just are looking for 400 gigabits per second bidirectional throughput.
Just real quickly, I apologize if I missed it. CPS.
Yeah, I was wondering the same thing.
So
you say perform similar at smaller CPS.
Yeah.
CPS.
Okay.
Yeah.
Sorry, say it again.
Connections per
Connections per second.
Yeah.
Thank you.
So these are the results of comparing the behavior of these two data path acceleration pipelines. So we have OVS Doka hardware offload and OVS kernel TC hardware offload. And you can see here very, very similar performance in terms of throughput, right? This is exactly what you would expect because essentially you're offloading as much of the data path as possible onto the hardware. And you just look here on the right-hand side on the server core utilization, we can measure the efficiency of the Doka kernel bypass mechanism relative to the OVS kernel TC hardware offload. You can see that we're using more cores in the OVS kernel mode, and we're super efficient on OVS Doka. But that's not the whole story, right? We really need to test what happens with stateful traffic. And this really can stress the system, whether it's NVIDIA's implementation or it's the kernel implementation with the OVS kernel module. But in this very simple thing, you can see that we're very, very close in performance still at about 25,000 connections per second. This is where we're actually leveraging both NAT and potentially access control list rules. But Doka achieves this performance, initially this ramp up in connections per second much quicker. It takes OVS kernel a bit longer. If you're monitoring the performance of the underlying kernel, you're going to see a lot of spin lock happening. There's a lot of work still being done on the kernel side with OVS Doka, and the kernel bypass is just a single CPU core that we reserve for this purpose. And that's what gives us a lot of determinism. In this example here, we're actually testing with very, very small payloads. So we're able to really stress the interaction between the hardware and the driver.
Just a quick point on that. Since the connections per second terminology came up, if you think of applications, right, most of these issues will open a tremendous numbers of connections to serve their purposes. Nowadays, modern applications, right, they would continuously be chattier, small packets, small TCP connections, but it's a complete stream of connections continuously, right? So that's why this is something that's not always tested because people, like I said, layer 2, 3, forget layer 4, 7. So that's when you start looking at small packets, small transaction that happens in real life, you start seeing certain levels of problems that gets exposed, and as early in the life cycle that it can get exposed, the earlier it can be fixed.
Yeah, so those types of performance tuning is really important, noticing the difference between these two lines. The blue line here is showing a lot, a lot less determinism in the system at scale. this is really important to our customers. Our customers want some sort of like, you know, deterministic band in which the performance of the system will remain. So for example, if we can say that, you know, the system will remain under, you know, 1 millisecond, that might be completely fine. They just don't want, you know, a delta happening where you might be 1 millisecond and then spike into 15 or 30 based on the load that's on the system. Also the fact that some of the systems are actually multi-tenant. So you don't want a noisy neighbor problem. You don't want somebody that's co-resident on the same machine causing an issue for you. You can see here again that at these sort of connection per second rate with the work that's going on in the kernel, that in the OVS kernel with TCA hardware offload, you're using a lot of cores because there's a lot of data path rules being programmed in the software data path and in the hardware data path. And this causes like a lot of like OVS's revalidation to happen, and you're using a lot of cores to maintain that. So around 28 less cores under this profile, but that's not enough. So we want to go to 50K, right? And you can really start to see the performance deltas appearing at these much higher rates. OVS Doka is able to get to the target objective much quicker. OVS kernel initially struggles. What's happening in this white space between these green and blue lines is like there's a lot of connections probably failing. Yeah, go ahead. Yeah.
Yeah, how did you choose 450K as the payload size for this testing?
Yeah, it's a good question because like we're trying to keep the packet size small. So we want to basically stress the interaction between the software path and the hardware path so that the driver has to do a lot of work to figure out when I should hand off to the hardware to program the E-switch.
Oh, I was just going to ask, do you have some real one numbers that what's a typical packet size and or connections per second that you're seeing in an AI training scenario or an AI inferencing scenario to give us sort of how do we relate this back to the real world?
Okay, so in the real world, number one, we don't know ahead of time. Every workload is different. This front-end networking is not used for training.
Okay.
Right? So you typically, we have InfiniBand implementation on the back end, so all GPU to GPU is highly optimized using InfiniBand transport. Of course, there is Rocky, and Rocky is RDMA over converged Ethernet. You know,
last.
Okay, you're learning this week. Yeah, so on these workloads, what is it that we're really focused on? It's that movement of data from external sources into the system to feed you have a storage cache or some caching layer built locally on the system, and that's feeding the GPU because they're so data hungry. You need to have that sort of cache there, right?
Would it be fair to say that really all of this is you're really trying to figure out how to optimize your environment as best as possible for a customer whose workload you have an idea that it's going to be something, but you're not sure exactly what, other than it's going to be very high performance demanding.
Yeah, I mean, I would love if you came to me as a customer like 6 months before and told me exactly what you want to do, because then we could work together to build exactly what fits your needs. But as a cloud provider, right, we sell on demand. So you can come to us and you can say, well, I'm going to run this workload. Why, can I not just run this and not have to change anything, right? So being like really fast in terms of like delivering GPU capacity to customers to have all of the services we need around that, whether it's block storage, file storage, S3, whatever it is, everybody's somewhat different. Nobody does exactly the same thing. So we try to build the system, and this is part of this testing methodology, is like, number one, we want to understand the absolute performance of the system. We want to pull it completely to pieces in the lab. We want to validate it, test it, and as part of the testing process, we want to run those tests for long periods of time. Why? Because we want to ensure both stability. We want to check this. There are memory leaks somewhere maybe over time. So some tests might run 48 hours, 72, whatever it is that we decide, but the sole motivation is to understand what the upper bounds of system performance are, so that we can be very transparent with customers and show, here's the data of the performance of our system. Now you can come on the back end and you can do some nickel tests, or you can train a reference model, and you can look at the performance of the InfiniBand fabric. But different customers actually do multiple different degrees of, parallelism in the back end. So, there might be tensor parallel, data parallel, pipeline parallel. Everybody's somewhat different. Sorry for the long-winded answer.
No, I
but
think that's a great answer. It really helps set the context.
Okay, so I kind of a follow-up question is, but I mean, if you're opening this as a TCP connection, why are you only doing one transaction per connection?
Because that's the most stressful on the driver. So essentially, what you want to do is you want to basically.
Okay, so you don't want to hold the stream open.
Yeah, you could hold the stream open, but what's it really telling you about the performance of the system? These tests, again, are contrived to really exercise the worst possible case.
Yes.
And that's why, SciPerf is very good for us, because it allows us to control those knobs. We actually do tests where we do multiple different transactions, but the most interesting ones that tend to break the system. And again, I work very closely with the NVIDIA DOCA team on this. They're very interested in what it exposes about the optimizations they need to make in their software pipeline.
In what instance would you be, with NVIDIA and GPUs, would you actually be doing this kind, stressing it in this level, in real application environment?
In a, you tend to not want to see these workloads.
You understand that, but you're testing to this workload, so clearly you're seeing this somewhere.
So what we're trying to see is that as we put a system like this into production, that we can basically set a set of thresholds for the system. So for example, if a customer is inferencing on a system and that was exposed to the public internet, or they left a port open accidentally, and all of a sudden they get hit by a DDoS attack, and they start getting smashed with thousands of connections per second. Number one, that we know how to track, this metric. And number two, that when we hit a threshold, we want the dashboard to go red and we need to swing in and make sure that there is not something happening with the customer workload.
Beyond a denial of service, is there that kind of peak threshold that maybe it's 75% of this number that you're seeing them hit in the environment, the AI training environment?
No, we don't see that, those sort of rates today. But again, it's if you get some customer that imposes that workload at some point in the future, we want to be ready.
Do you even
part of our
going
engineering.
to see that? And if you saw that, what would be that? I guess what I'm saying, I'm looking at here is that AI is pushing everything we have.
Mm-hmm.
And you're testing at this level of, what NASA and those kind of people, the worst scenarios, right? What could blow up on the whatever. And so then you're saying, okay, so where would those thresholds, what thresholds do you see on the horizon that practically customers really need to be planning for over the next 4 to 5 years?
Yeah, so there are examples where if you implement this technology as, say, a gateway service, like the type of workload that gateway service is going to be serving is like a load balancer endpoint. So there could be a massive convergence of traffic on a system that serves, say, a load balanced endpoint. And that could be, hey, we have a really popular model that people love inference in. It might be DeepSeek, it might be something else.
Yeah, I was going to ask if you do congestion testing, because that's kind of what I would think of as another potential load that you would hit, where you would potentially start dropping a packet every now and then and have to deal with the retransmissions to figure that out. Do you do that type of testing as well?
Yes. So it's really understanding that performance. So again, as we're a multi-tenant environment, so in some cases you have multiple tenants on the same system. We need to be able to, number one, set metering thresholds for each customer. As an example, as part of this testing, we will push each tenant workload to the set parameters that we give. And that ensures that, number one, that if a customer really uses up or eats all the resources that they have available, that they don't bleed over and steal someone else's resources. And it's those types of things. I think like quite humbly, I learn about new things every day when building this infrastructure. It's complex. Like I said before, it's like we don't know ahead of time what the customer is going to do, but we just want to really understand where the breaking points in the system are.
Okay.
Yeah.
This is a good example. I was just wondering what else you'd tried.
Yeah.
Jim Sprinsky, CDC. Yeah, I was just thinking about this because of all the different things you might have to deal with, everything from like a smart meter output, or I'm thinking about that wind farm that you showed out in the ocean. What happens if a storm comes up in the North Sea, right? And now suddenly you've got horrendous amounts of data coming in from the turbines because you're getting close to them exceeding their capacity, or maybe, hey, we need to shift them so that they're feathered or whatever it could be, right? Or even things like EVs suddenly having to charge at much higher rates because it's winter time, as we had in Chicago a few years back. And, so this is, but I love the fact that you're, looking, okay, what's the worst possible thing and planning for it, because having been in that situation before where we didn't plan for it, I would have loved to have some sort of tool like this and know that my system could handle it.
Yeah, I mean, it's a good example here is the work that we did initially, brought NVIDIA and Keysight a bit closer, because as working with the NVIDIA team, they were like, wow, you're able to really break our system. Let's use your same testing methodology to actually test internally. Now they've integrated a lot of this into their automated testing pipeline. So we work closer together. They learn from us, we learn from them.
Yeah.
We partner with Keysight, and we really can drive, forward value for ultimately customers who are investing a lot of capital into paying for this infrastructure. We need to give them a world-class service. We can only be world-class operators when we know what the absolute limit of any system is.
Goes to my last slide. Don't let your users be your beta testers. So that's what Crusoe is doing different here.
Yeah, so the last call out really is like it took, OVS kernel about 5 minutes to stabilize at the same connection rates. This is the outcome that we're really after. We don't stop here. We go beyond this. We're going to try and get to 8 million connections in hardware, hopefully into the hundreds of thousands of connections per second. And this is the latency profile here. You can see this green line is exactly where we want to be. We don't want this non-determinism in the system. We're able to eliminate that. And yeah, from our point of view, we were too small to go and try and build our own traffic generator. Having worked with Keysight many times before, this is what these guys do, an emulation company. It's massively beneficial now for us and our customers.
Cool.
Just what's next for us, we'll get the Blackwell platforms on our cloud platform. We'll keep advancing our telemetry and monitoring as we roll a system out into production. And we're still massively focused on storage optimization and scale, and of course security is like at the front of mind for us.